You know, in medicine, we spend a massive amount of time worrying about flow, just keeping the pipes open.
Right.
But when we talk about a blockage, an acute MI, a stroke, a massive pulmonary embolism, we usually focus on the immediate disaster.
The traffic jam.
Well, yeah, because the supply line is cut. Oxygen isn't getting to the brain or the heart. Time is tissue, as they say. But today, for this deep dive, I want to look at the cleanup crew. We're looking at a stack of research on fibrinolytic therapy.
Mm-hmm.
And I think we need to draw a hard line in the sand right away, because people often lump these in with blood thinners. But we aren't talking about anticoagulants here, are we?
No, and that is probably the single most important distinction to start with.
Okay.
Anticoagulants, things like heparin or, the oral drugs that target factor 10A, those are preventative.
Right.
They stop the clotting cascade from adding more bricks to the wall. They stop the pileup from getting worse.
So an anticoagulant prevents the mess from growing, but it doesn't clean up the mess that's already there.
Precisely. Fibrinolytic therapy. These are the clotbusters. We aren't managing the traffic. We are blowing up the roadblock. We were talking about drugs that hijack a very specific, very potent biological mechanism to physically dissolve a thrombus that is already killing tissue.
It's the difference between a crossing guard and a demolition team.
That's a really fair way to put it. And as the research shows, the evolution of these drugs, from bacterial extracts to genetically engineered enzymes, it's basically a history of us trying to control that explosion.
Because if you use too much dynamite...
You don't just clear the road, you take out the whole city.
Let's talk about delivery then. Because looking at the sources, it seems like the strategy really changes based on where the problem is.
It depends entirely on the geography of the problem. For the catastrophic, life-threatening stuff, a heart attack, an acute ischemic stroke, we usually go systemic.
Just an IV?
An IV line, yeah. We flood the bloodstream because we need that drug to reach the brain or the heart immediately. Speed is the only metric that matters.
But I saw, for things like deep vein thrombosis, DVT in the legs, the approach is different, more targeted.
It is. In those cases, we can be more tactical. A doctor might use catheter-directed therapy.
So they thread a wire right into the clot.
Exactly. A catheter with side holes right into the clot itself. It's like injecting the agent directly into the rock slide rather than spraying it over the whole mountain.
And sometimes they even use little devices to break it up.
Yeah, they combine it with mechanical fragmentation while the drugs work.
Okay, so that's delivery. Now the mechanism, this is where the biology gets pretty heavy. The literature keeps talking about it, Zamagen. Specifically, plasminogen.
Exactly. Think of plasminogen as a sleeping giant. It's totally harmless, just floating around in your blood.
Until something wakes it up.
Until an activator like TPA comes along. Once it wakes up, it becomes plasmin. And plasmin is the engine. It's what actually chews up fibrin, the mesh that holds a clot together.
Okay, but here's where I got stuck looking at the numbers in the source material. I was doing the math on the regulations, the breaks, and it seems, well, dangerous.
Ah, you're talking about the inhibitors.
Yeah, the anticlasmin. It's there to stop plasmin if it goes rogue. But the ratio...
You notice the concentration levels.
I did. The concentration of plasminogen, the potential explosive, is 2 times higher than its inhibitor. A 2-to-1 ratio. I mean, that feels like a massive design flaw.
It does seem counterintuitive, doesn't it?
It's like if you hit the gas pedal all the way, the brakes literally cannot stop the car.
And you've just pinpointed the exact physiological risk. If you were to activate all the plasminogen in your circulation at once, you would completely overwhelm those inhibitors.
That's the systemic little disc state.
That's it. It sounds technical, but what it really means is that the plasmin stops just targeting the one bad clot.
And starts eating clotting factors everywhere else.
Everywhere. You just tank your blood's hemostatic potential. Suddenly, old IV sites start oozing, your gums bleed. You risk a major internal hemorrhage. You basically lose the ability to keep your blood inside your vessels.
So, if the math is rigged against us, why don't we just dissolve every time we get a bruise?
Because the body is smarter than that. It refuses to play that game out in the open bloodstream. It changes the rules by forcing the reaction to happen on the clot.
The ternary complex that was mentioned in the research.
Yes, exactly. The activator and the plasminogen, they meet up and bind directly to the fibrin surface. It's a localized team-up.
And that protects them.
It does. When plasmin is generated right there on the clot, it's shielded. The inhibitors can't really get to it effectively.
So it's like a force field.
Yeah.
Inside the clot, the demolition crew is safe to work. But outside, in the open blood.
The inhibitors swarm any stragglers, and it gets even cleverer. As the clot starts to break down, the broken ends of the fibrin act like little sticky magnets. Chemical magnets. The literature calls them C-terminal lysine residues. When these are exposed, they attract more TPA and more plasminogen right to that spot.
Wow, so the destruction actually fuels itself. It's a positive feedback loop.
Precisely. It accelerates the process exactly where you need it, and nowhere else.
Which brings us to the pharmacology. We have drugs that try to mimic this to save people from strokes, but it seems like some drugs respect this magnet system and others just ignore it.
That is the perfect way to put it. It's the difference between a sniper and a shotgun.
Okay.
You have fibrin-specific agents, like Alteplase. They look for those fibrin keys, those magnets we just talked about. They only activate plasminogen that's already bound to the clot.
So the sniper.
Yeah.
Keeping the action contained.
Right. But then you have the older drugs, Streptokinase, Urokinase.
The shotgun approach?
Exactly. They are non-specific. They don't care about location. They just activate any plasminogen floating freely in the blood. And remember your math problem.
The 2-to-1 ratio. If you activate all the free-floating stuff, you easily overwhelm the brakes.
And you trigger that systemic lytic state. By ignoring the body's natural strategy, those drugs create unopposed plasmin in the circulation. Sure, it clears the clot, but the risk of collateral damage just skyrockets.
Let's talk about streptokinase.
The old guard.
Which comes from streptococcal bacteria, the same family as strep throat.
The very same. And because it's bacterial, it functions differently. It's not really an enzyme that cuts the protein itself.
So what does it do?
It operates by, I guess, brute force. It grabs a molecule of plasminogen and physically twists it. It forces a conformational change to expose the active site.
It bullies the molecule into working.
It does. But here's the major flaw. Streptokinase has zero affinity for fibrin. It could not care less about the clot. It just grabs any plasminogen it finds in your arm, your leg, floating in the plasma, and activates it.
So it immediately triggers that systemic lytic state we just talked about.
Immediately. It's completely nonspecific.
Right.
And there are other dirty aspects to it. Because it's a bacterial protein, your body recognizes it as an invader.
So we make antibodies against it.
Yep. If you've had a strep infection or if you've had streptokinase before, your body might just neutralize the drug before it even does anything.
And the allergic reactions?
About 5% of patients. Fever, chills, rashes. Plus, the sources mention transient hypertension, low blood pressure.
Why would a clot buster drop your blood pressure?
It's a side effect. When you release that much plasmin systemically, it triggers the release of something called bradykinin.
Which is a vasodilator.
A potent one. It opens up your blood vessels and your pressure drops. It's usually manageable, but it's another complication you don't need.
Now, there was an attempt to fix this with Anistreplase, but reading the description, it just sounds like they put a hat on streptokinase and called it new.
It was a bit more sophisticated than a hat, but yeah. They took the streptokinase plasminogen complex and chemically attached an anisoyl group over the active site.
They keep it quiet.
Well, to give it a longer half-life, the mask falls off slowly in the blood. This meant you could give it as a single injection, a bolus, instead of a slow drip.
So it was convenient.
Very convenient, but mechanistically. Still streptokinase, same bleeding risks, same allergic reactions.
So we finally move from the bacterial sledgehammers to human biology. Urokinase from kidney cells, and then the real pivot point, Alteplase, or TPA.
A recombinant tissue-type plasminogen activator. This was the game changer. We finally engineered a human protein to do the job.
The structure of this molecule is...
Yeah.
It's wild. The source material describes 5 domains, and I love the names, a finger domain, an EGF domain, and 2 crinkle domains.
Like the pastry. It literally looks like the pastry.
So these shapes aren't just for show.
Not at all. The finger domain and that second crinkle domain are what give Alteplase its affinity for fibrin.
So unlike streptokinase, this one actually wants to bind to the clot.
It does. It works 2 to 3 orders of magnitude better in the presence of fibrin than it does in free blood. It is fibrin specific.
But, and this is where I want to slow down.
Yeah.
Because the biology gets tricky. It's specific, but it's not perfect. The notes mention something called DDE.
Right. This is the nuance that separates the textbook from reality. Alteplase binds to fibrin, yes, but it also binds to DDE.
And DDE is...
It's the debris of a clot that has already started to dissolve. And the problem is, Alteplase can't really tell the difference between the solid clot and this debris floating around.
So the drug gets confused by the wreckage.
In a way, yeah. The DDE stimulates the Alteplase to activate plasmin, even away from the main clot. And here's where it gets dangerous. This misplaced plasmin starts breaking down fibrinogen into something called fragment X.
Fragment X. Sounds ominous.
It acts ominously. Fragment X is this high molecular weight breakdown product. The issue is your body tries to use fragment X to build new clots. You know, the little plug stopping minor leak.
But it's defective material.
You're building a wall with crumbling bricks.
Yeah.
Exactly. It makes your normal hemostatic plugs susceptible to lysis. They fall apart.
Wow.
And that's why Alteplase can still cause significant bleeding, despite being specific. The drug gets tricked by the debris, it creates fragment X, and that compromises the body's ability to patch itself up.
That is a fascinating failure mode.
It shows just how interconnected these systems are. You pull one thread, and a knot comes loose 3 steps down the line.
So Alteplase has better survival rates than Streptokinase, but it needs a long infusion, 60 to 90 minutes. Which brings us to the next generation, Tenecteplase and Retiplase.
This is the era of genetic refinement. Scientists looked at the TPA molecule and asked, how do we fix the bugs?
Let's start with Tenecteplase, TNK. This seems to be the gold standard in the current literature.
TNK is a masterpiece of protein engineering. They made 2 key modifications. First, they added a sugar chain glycosylation to one of the Kringle domains.
And the sugar acts like a shield.
It slows down clearance by the liver, which means you can give Tenecteplase as a single bolus. 1 quick injection, 5 to 10 seconds, and you're done. No 90-minute drip.
That's massive for logistics in an emergency.
Huge. But the second modification is even cooler. They did a tetraalanine substitution. They just swapped out 4 specific amino acids.
And this was to deal with that inhibitor, PAI1.
Correct. This change basically puts the drug in stealth mode. PAI1 can't lock onto it as well. So Tenecteplase lasts longer and it ignores the brakes.
And what about that fragment X problem? Is it more specific?
It is. It has higher fibrin specificity and it binds less to that confusing DDE debris. The trials showed that it causes significantly fewer non-cerebral bleeds and reduces the need for blood transfusions.
Okay, so TNK is the elegant solution. Then we have Retiplase. And reading the breakdown, it honestly sounds like they just took a hacksaw to the molecule.
It is a bit drastic. They literally chopped off the finger domain, the EGF domain, and the first Kringle domain.
But wait, we said the finger domain is what grabs the fibrin. If you cut off the finger, how does it hold on?
It doesn't hold on very well. Retiplase has a much lower affinity for fibrin than TPA.
So?
Yeah.
Why would you do that? Why make a worse molecule?
2 reasons. Production costs and pharmacokinetics. Because they chop so much off, it's a smaller, simpler molecule. They can grow it in E. coli bacteria.
Back to bacteria again.
Back to bacteria. And because it's grown in bacteria, it doesn't get glycosylated. It doesn't get that sugar coating that TNK has.
And usually, no sugar means the liver clears it out instantly.
Usually, yes. But here's the paradox. The structural changes, chopping off all those domains, made the molecule behave strangely. Even without the sugar shield, it actually has a longer half-life than the original Alteplase.
That seems like an accident.
It's a bit of a quirk. It lasts longer than TPA, but not as long as TNK, so you have to give it in 2 separate shots about 30 minutes apart.
It feels like the store brand version.
In a way, the data says it's at least as good as Streptokinase, comparable to TPA, but it just lacks the elegance and the improved safety profile of Tenecteplase.
So if we trace this whole timeline, we started with a bacterial protein that just causes chaos. We moved to a human protein that's smart but gets confused by its own success. And now we have a genetically modified version that's faster, stronger, and more precise.
It's a remarkable progression. We are literally editing molecules to fit the specific needs of emergency medicine.
But it all comes back to that balance you mentioned right at the start.
It does, the balance between clotting and blading. It is arguably the most delicate high-wire act in medicine. Clot too much, you die from ischemia. Dissolve too much, you bleed out.
And these drugs are our attempt to walk that wire.
With a safety net, but the wind is always blowing.
It really just highlights how difficult it is to out-engineer evolution.
And yet, biology always finds a way of, changing the locks on you. That fragment X issue with Alteplase, it still haunts me. We built a drug to target fibrin, only to find out the body creates a breakdown product at DDE that mimics the target perfectly.
It's a decoy.
It is. It tricks our sophisticated drug into activating in the wrong place, breaking down the wrong proteins, and causing the very bleeding we're trying to prevent.
It makes you wonder if perfect specificity is even possible in a system this messy.
That's the question, isn't it? Are we smart enough to untangle a web that has been evolving for millions of years, or Will there always be a side effect, a decoy, or a fragment X waiting to trip us up?
A humbling thought. Thanks for diving deep with us on fibrinolytic therapy. We'll see you on the next one.